Welcome to our lecture on linear models. Today we are going to tackle a very important topic, the violation of normality assumptions. Imagine you are a teacher grading a final exam and you decide to grade on a curve. That curve assumes most students get an average score, forming a symmetrical bell shape. But what if the exam was incredibly difficult and the scores are completely lopsided? Your standard grading system would break. In linear regression, we face a similar issue. We will explore what happens when our model's errors do not follow that perfect bell curve, why it matters, and the mathematical tools we use to fix it. Now that we have our grading curve analogy in mind, let us look at how this applies to regression. In a standard linear regression model, we make a core assumption that the error term follows a normal distribution. Why does this matter? Because the error term, which we often call the residual, represents the leftover difference between what our model predicted and the actual real-world data point. If our model is doing its job correctly, these mistakes should be random and balanced. A normal distribution means that if we plotted all these errors on a graph, they would form a perfect symmetrical bell curve, centered exactly at zero. This symmetry is what allows us to make reliable statistical promises. So, what exactly happens when this assumption is broken? A violation of the normality assumption occurs when the true distribution of these errors is skewed to one side or has unusually fat tails, meaning there are too many extreme outliers. It simply means our model's mistakes do not balance out in the predictable way we expect them to. The interesting part is that the core line of best fit might still be perfectly accurate. However, the probability distributions we rely on for hypothesis testing and calculating confidence intervals become completely invalid. We lose our ability to trust the statistical significance of our results. Before we move on to diagnosing these issues, let us look at the strict mathematical representation of this assumption. The formula states that epsilon is distributed as n with parameters 0 and sigma squared times I. Let us break that down. The symbol epsilon represents the vector of error terms, which are the unobserved random disturbances in our data. The tilde symbol means is distributed as. The letter n stands for the normal distribution, our classic bell curve. Inside the parentheses, the 0 indicates that the average of all errors is exactly 0, meaning no systematic over or under prediction. Finally, sigma squared times I represents the variance-covariance matrix, where sigma squared is the constant variance and I is the identity matrix, ensuring each error is independent. If the errors deviate from this exact setup, the assumption is violated. Now that we understand the mathematical definition, how do we actually detect if this assumption is violated in practice? We cannot just guess. We need specific diagnostic tools. The primary visual diagnostic tool is the quantile-quantile plot, commonly referred to as a QQ plot. A QQ plot takes the sorted residuals from our fitted model and plots them against the theoretical quantiles of a perfect normal distribution. Think of quantiles as data points divided into equal-sized groups. If the normality assumption holds perfectly true, all the points on the QQ plot will fall exactly along a straight 45-degree diagonal line. However, if the assumption is violated, the points will curve away from the straight line, often forming an S shape or a U shape. Let us see this visual diagnostic in action. Here, you are looking at a standard QQ plot. The horizontal axis represents the theoretical quantiles of a perfect standard normal distribution, while the vertical axis shows the actual sample quantiles, which are our model's residuals. Notice the straight dashed red line running diagonally? That line represents perfect normality. Now, look at the blue circles representing our data. In the middle, they track the line fairly well. But look at the extremes. On the far left, the points dip below the red line, and on the far right, they rise above it. This creates a distinct S-shaped curve. This visual curvature immediately tells us that the errors have heavy tails, prompting us to take corrective action. So, we have diagnosed a violation using our QQ plot. What is the next step? When we confirm a violation of normality, the most common and powerful way to fix it is by using the Box-Cox transformation family. I want to emphasize the word family. The Box-Cox transformation is not just a single formula, but a whole flexible family of mathematical adjustments applied to the dependent variable to force its errors into a normal shape. It is controlled by a single tuning parameter, denoted by the Greek letter lambda. By testing different values of lambda, a computer algorithm finds the exact mathematical transformation that makes the data's error distribution as close to a perfect bell curve as possible. Let us look at the mathematics behind this family of transformations. This piecewise equation defines the complete Box-Cox transformation. The term y superscript lambda in parentheses represents the new, transformed version of our original dependent variable. The original variable is y, which must be strictly positive for this math to work. The parameter lambda dictates how aggressively we reshape the data. When lambda is not equal to 0, we use the top formula, raising the data to a power, subtracting 1, and dividing by the power. However, through the mathematical rules of limits, as lambda approaches exactly 0, the formula perfectly simplifies into the natural logarithm of y, shown in the bottom case. By simply changing lambda, we can apply square roots, inverse transformations, or logarithms seamlessly. Now that we have our formula, let us see this with a concrete example. A researcher is modeling the salary of corporate employees based purely on their years of experience. We start with our initial, unmodified linear regression model, where y is salary and x is experience. After fitting this initial model, a QQ plot reveals that the residuals are heavily right-skewed. This means a few executives with massive salaries are stretching the error distribution, making our p-values untrustworthy. To fix this, the researcher runs a Box-Cox analysis, and the software determines that the optimal transformation parameter, lambda, is exactly 0. We now need to apply this specific transformation to fix our model. Continuing with our salary model, we know our optimal parameter is 0. Looking back at our Box-Cox piecewise function, the rule states that for a parameter of 0, the transformation simplifies perfectly to the natural logarithm. Therefore, our strategy is to take the natural logarithm of every single salary value in our dataset. By doing this, we compress those extremely high executive salaries, pulling the long right tail of the distribution inward and forcing the data into a more symmetrical, bell-shaped curve. This gives us our final transformed regression model. The original dependent variable is replaced by its natural logarithm, and our new error term, denoted with a star, now follows a perfect normal distribution, making our hypothesis tests valid again. Let us look at a second example, where the parameter is not 0. A chemical engineer is modeling the yield of a chemical reaction based on the temperature of the reactor. The residuals from the initial linear model show a mild violation of normality, appearing slightly skewed. The engineer runs a Box-Cox optimization routine, which calculates that the best transformation parameter to achieve normality is lambda equals 0.5. Because the parameter is not 0, we cannot simply use the natural logarithm like we did in the previous example. We need to apply the primary Box-Cox formula. Continuing with our chemical yield data, we must use the top part of the Box-Cox piecewise formula designed for non-zero parameters. We will substitute the value of 0.5 directly into the formula. We replace every instance of the Greek letter lambda with the numerical value of 1/2. The numerator raises our original yield data to the power of 1/2 and then subtracts 1. The denominator is simply the parameter value itself, which scales the entire transformation appropriately. Now, we just need to simplify this mathematical expression to use it in our updated regression model. Let us simplify that expression. Raising a number to the power of 1/2 is mathematically identical to taking the square root of that number. Furthermore, dividing any value by 1/2 is exactly the same as multiplying that value by 2. This simplified version clearly shows that a Box-Cox transformation with a parameter of 1/2 is fundamentally just a scaled square root transformation. This gives us our final corrected regression model for the chemical reaction. By applying this specific square root scaling, the new error term on the right side now conforms to the required bell curve shape, allowing the engineer to calculate accurate confidence intervals. Now that we have used this formula, let us understand why correcting these violations is absolutely critical in the real world. In fields like medicine, finance, and engineering, statistical guarantees matter. If you ignore a severe normality violation, your model might calculate a confidence interval that is far too narrow, leading you to guarantee a result that is actually highly uncertain. This false confidence can cause a pharmaceutical company to approve an ineffective drug or a bank to underestimate its financial risk. However, there is a silver lining. For very large sample sizes, a statistical rule called the central limit theorem often saves us. Because of this theorem, minor violations of normality become less dangerous as you collect more data, making this assumption slightly more forgiving than others. We have covered a lot of ground today, so let us summarize the key takeaways. First, remember that the normality assumption requires the errors of a linear model to follow a symmetrical bell curve. Second, while the line of best fit remains unbiased, even if this assumption fails, all your hypothesis tests and confidence intervals become unreliable. Third, we visually diagnose these violations using QQ plots, looking for any S or U-shaped deviations from a straight diagonal line. Finally, when a violation is found, we fix it by applying the Box-Cox transformation family, which uses a tunable parameter to reshape the data into a normal distribution. You now have the tools to ensure your statistical models remain robust and trustworthy.